Good evening, everyone. We are in the week 8 problem solving session of the course Digital Controller in Switch Mode Power Converters and FPGA-based Prototyping. Week 8 is about digital controller implementation using fixed point arithmetic and Verilog HDL. Let me share my screen. Can you see my screen?
Visible, sir.
Okay. Okay, we are in the week 8 of this course, and week 8 is about digital controller implementation using fixed point arithmetic and Verilog HDL. So till now, whatever we have learned, we will utilize that concept, all the models, and the Verilog that we have learned last week to write a closed loop control for the buck converter, different types of control techniques like voltage mode control, current mode control. And before going into the week 8 outline, let me summarize what we have discussed in week 7. So week 7 is like a building block for week 8. So week 7, we have learned whatever Verilog that is necessary to write a digital controller code for week 8 or upcoming weeks. So whatever Verilog that is necessary that we have discussed in the last week. So week 7 was about introduction to Verilog and simulation using Xilinx Webpack. So we have discussed about Verilog and Ripple carry adder, and then we have seen the simulation how we can use the Xilinx ISA software. So just to summarize what we had discussed. So in the beginning, we had discussed about the introduction to Verilog HDL. So how to write a code, why we are choosing Verilog, and how to write a module, what is a module, and what are the different design flow that is available in Verilog, and what are the different data types that we are going to use for the digital controller implementation, and what are the different modeling and description styles that are available in Verilog HDL, what is non-blocking statement, what is blocking statement. So blocking versus non-blocking, and how they create, what is the difference between them, how the values will change if you write in blocking, and how the values will change if you write in non-blocking, and what is the syntax. All those things we have discussed. And then we have discussed about the expressions and operators that are available in the Verilog HDL. Then we have discussed about the ripple carry adder. So in ripple carry adder, we have discussed, so before we write any code, so we have to actually design it. So we had discussed about the top-down approach. So top-down design approach of ripple carry adder, where we have realized ripple carry adder using full adders, and then full adder using half adder, and then half adder using gates. So then using the same logic, we have implemented the Verilog. So whenever we are going to write something, so first we have to fix the architecture, say in the terms of block diagram or timing diagram, then only we should start writing code so that we can debug easily. And then we'll check whether the code is right or wrong using the simulation. Xilinx ISC is widely used, and whatever FPGA that we are using, it needs Xilinx ISC software. But if you are using some higher or latest version, then you might have to use Vivado software as well. So it depends upon which FPGA you are using. So they will tell which software you have to use. So software, the UI might be different, but the concept and everything remains same. And then we have discussed about binary numbers. So there are 3 different types of binary number representation that we'll be using in throughout this course. One is the straight binary, which is also unsigned. And in signed, we have 2 different representation. One is the 2's complement, and the other one is the offset binary. So these 2 are signed. And then we have discussed about fixed point arithmetic as well as Q format. So this is actually very crucial topic. So here we were getting the quantized analog voltages. So if a Q format is fixed, what is the quantized analog voltage? And Q format we have discussed, it is a virtual dot. So the FPGA will not see the dot. Only for us humans to understand what is the quantized analog voltage, we'll put a virtual dot there, and then we write the code accordingly, so that we'll be aware of the quantized analog voltage and we can better understand and debug. But the like simulator will see it as a 10-bit number, but we are putting a virtual dot and saying Q4.6 or Q1.8, which we'll be discussing again today in detail while we discuss about the code. And then we have discussed about counter-based DPWM. So how to write counter-based DPWM and how to insert dead time and what is the logic for dead time. And we have seen in the simulation as well that dead time is coming or not. And here we have given 6 cycles of 100 megahertz clock. So 6 cycles of 10 nanosecond. So it is 60 nanosecond, but it is not a thumb rule that it should be 6 cycles. Depending upon the application, it should be like designed how much should be the dead time, and then accordingly you should insert the dead time, and we should check whether the dead time is working or not. Else, if there is any short circuit, uh, like in the case of buck converter, what I mean to say is, so the high side and low side switch should never be turned on at a time, else it will be short circuited and the switches will get damaged. So this will happen. So that's why we are putting that time, so that whenever both the switches are off, the diode will conduct through this path, and we should not also increase the dead time, then the diode losses will increase. And then we have solved some problems on in understanding the Q format, fixed point arithmetic, binary numbers, all those things. So coming to the week 8. So week 8, from week 8, we will discuss about the actual hardware implementation of different control techniques. So week 8 is about digital controller implementation using fixed point arithmetic and Verilog HDL. In week 8, Sir has discussed 3 modulation techniques. One is the digital voltage mode control, and the other one is mixed signal current mode control, and digital PSM. So all these are fixed frequency. Variable frequency will be discussed in the upcoming weeks, 10 or 11. And also there is something called multi-mode. So all these things will be discussed. But these are the basic, because these are fixed frequency, and fixed frequency will be much easier than variable frequency. Variable frequency, we have some other additional blocks like minimum on time, minimum off time. So all these things. So these are very crucial, and these are the basic control techniques. So to start with, we'll start with the digital voltage mode control. So in today's session, I'm planning to discuss as shown. So first I'll be discussing with the digital voltage mode control. So top-down design methodology, what is the practical implementation, what are the practical gains, why we are considering that, and how. So again, SAR has discussed first the architecture, and that architecture SAR has converted into Verilog HDL implementation, and then it is written in Xilinx IC software, and then SAR has checked the performance in the hardware, and hardware results are also shown by SAR, which I will also be showing. And the second part is the mixed signal current mode control. Again, here we'll show the top down design methodology. What is the practical implementation? Because whatever we simulate, it is only an ideal case, but in the case of actual practical hardware, we need to consider some more aspects, which we'll be discussing when we come across this part. And the third one is the digital pulse skipping modulation, or digital PSM. So this is mainly for the light load conditions. So the converter was operated at very light load. So let me change the color. So say if the ripple is more, and the ripple is more and more than the average, and we don't want it to cross negative, so we were using something like this. So a charge pulse and a skip pulse. So this is to reduce the RMS, which will again reduce the losses. So loss reduction. We are going for the DCM operation mode, and one such DCM operation is PSM. SAR will discuss PFM in the upcoming weeks when he discusses about the variable frequency modulation technique implementation in Verilog. But as this week is only fixed frequency, so we are going for the fixed frequency light load modulation technique, and one such thing is voltage based digital PSM. So we are discussing that, and then we'll see the Verilog HDL implementation, how to write the code, and hardware results. And here we can consider some different case studies that Sar has considered in his lecture, and then we'll solve few problems at the end. So first thing is the digital voltage mode control, which we have discussed many times during the week 2 as well as MATLAB simulation as well as controller design. So the first part is design methodology. So we'll first see the architecture and see how this has to be implemented. And then we'll see the Verilog HDL, and then we'll discuss about the hardware results. So coming to the digital voltage mode control implementation, as we have already discussed, there is an ADC, which and that digital voltage will be subtracted from the V reference, which will give us V error voltage, which will be fed to the PID controller. And this will give the control voltage compared with the ramp, which will give the reset, and set pulse is the fixed frequency. And then it is going to the dead time, and dead time is giving high side signal as well as low side signal. So there is one additional block, if you have noticed here, which is this R1, R2. So we are stepping down V0 to V feedback. So if you see, V feedback is R2 by R1 plus R2 into V0. So why we are doing this? Because ADC has input span, right? So the voltage should be within, say, plus or minus 1 volt or plus or minus 2 volt. But my output might be, say, 3 volt or 5 volt. Then I cannot directly give that V0 to ADC because it is beyond its span, and it might damage the ADC. So I have to scale down it to some voltage that is inside this within this span, input span. Say it is 5 volts, then I have to step down to say 1.5 or 1 volt, depending upon the user requirement, so that it will not cross 2 volt. You have to consider all the case studies. Like when we are giving reference transient, we are giving from 5 volt to 6 volt. So we have to design R1 and R2 in such a way that even at the worst condition, it should not cross, say, 2 volt or 1 volt. Accordingly, we have to design R1 and R2. So for the safe side, we'll always choose very high gain or very small gain, so that it will never cross 1 volt or 2 volt. So for that reason, we'll put this feedback, and depending upon your V0, say your V0 is already less, then you might not need R1 and R2, you can directly feed it. But if your V0 is high, then they will put a resistor divider or some other differential op-amp circuit, and then they'll scale down to a lesser value so that it can be fed to a analog to digital converter, and then everything enters the digital controller. So this is the basic digital voltage mode control architecture that we have discussed in many weeks. So now coming to the Verilog module. So if we represent this as a Verilog module, so this is our code. So this is our main module code, main module Verilog code. And what are its inputs and outputs? So A to D is giving the digital data. So there is this analog to digital converter feedback voltage. So whatever scale down voltage that we have generated, that will go to the analog to digital converter, and this will give 10-bit analog to 10-bit digital value, which will go into the digital voltage mode control. So this is one input, and this analog to digital converter needs frequency FADC. So that is the output that this output of this block, you can say. So we have to generate this ADC from the FPGA, which will be fed to analog to digital converter. And then Qtran is for, say, reference transient, reference or load transient. So depending upon you want load transient or reference transient, SAR has given 1-bit option. So it can be either 0 or 1. I'm not sure. I think 1 is for load transient and another is for reference transient. Maybe 0 is for load. SAR has defined in such a way. And F clock is the main clock coming from the FPGA. So this is coming from the FPGA clock, which is 100 megahertz in our case. So it might vary from FPGA to FPGA. So if we are using any FPGA, maybe it might have different clock frequency, or maybe it will have the same clock frequency that you should consider while generating the other clock frequencies or writing the code. So the output, what we need PWM high and PWM low. So these two are going to the high side and low side switches. So one is going to the high side switch and other is going to the low side switch with dead time so that they'll never be shorted. And then other one is the Q load. So Q load is like this. So here we have shown only one resistor, right? Or maybe let me change the color. Just a minute. So here we have shown only one color, but in fact, it is not just one color. Sorry, not color. We have shown only one resistor, but in fact, it is actually two resistors. So let me use this color. So here we have shown only R, but it is not actually R. There are two resistors. So this is the output capacitor, and one is RC with a switch. So this is continuous resistor RC, and this is the switch resistor RSW, and the input to this is Q load. So whenever Q load is high, then RSW comes in parallel with RC, and this is much lower compared to RC. So the effective resistance will be lower. So current will be high. So whenever Q load is 1, we are increasing the load. Whenever Q load is 0, it is operating at light load condition. So Q load has two values. One is 0, one is 1. So 0 is for light load, 1 is for full load or high load. So that's how the results are taken, whatever results that SAR has shown. You are following, right? Everyone is following, right? Hello.
Yes, sir.
Okay. So this is the basic architecture. So now like these blocks are drawn. So these we can say Verilog module. So this is the structure of digital voltage mode control. Similarly, SAR has written or drawn similar blocks for all the other control architecture so that we can understand what is the input. So here we can see what are the inputs and what are the outputs. So we can get an understanding. So we can imagine the entire controller as a block, and these are the inputs and these are the outputs. So this is the same block. Now, if we actually see the voltage mode control architecture, so what is there inside this? So inside this module, what is there? So that is this block. And you can also put some another output is coming, which is Q load. So if we go inside this, so V naught is coming, KF is the gain. So we are scaling down the V naught and the gain is 0.27. So V feedback is 0.27 times V naught. Okay, now V naught is going to unlock to digital converter, and it has FADC coming from our main module. And so whenever SAR is using N, so say NX, so SAR is using this for a digital number. So here SAR is using N out. So N out is digital representation of output, or digital equivalent digital 10-bit number of V feedback. So N out is digital number, which is 10-bit. So this is being subtracted from N reference, which is the reference voltage in digital or binary number. The error is NE going to this PID controller, giving rise to NCON, the control voltage. And now this is being compared with the ramp. So this is the ramp. But we have discussed that in analog, ramp is smooth, whereas in the case of digital, ramp is a staircase. So from the main clock, we are using a counter to generate this ramp, and these two are being compared, giving rise to reset pulse, and set pulse is the switching frequency. Now this PWM, say QPWM is going to dead time block, and we have discussed this dead time block last week, which is giving rise to PWM high as well as PWM low. And another output is Q load. So this is basically the voltage mode control, and Q load is another pulse that we need, which is also present in the Verilog module. So this Verilog module should give us these outputs by taking these inputs. So till this point, it is clear, right? If you have any doubts, you may ask me. Okay, so now we are going to implement. Yes.
Sir, this FADC this FADC comes from where, sir?
So our main clock, or we can say we have one clock, F clock.
Okay, okay,
So this F clock
okay.
will should generate FHW, FADC,
Mm,
FDAC. So
mm,
our ADC needs a
mm,
FADC, which is the sampling frequency. So that has to generate, that should be given to the analog to digital converter, so which decides how fast it has to take the samples. And this everything comes from the F clock. So all these codes should be written in our Verilog code so that this will generate FADC, which will go to the analog to digital converter.
mm.
Okay.
Okay, sir.
Okay. Now we'll go into the Verilog HDL implementation. So coming to the main module, I will actually show you the Verilog HDL, then I will explain it here so that you can have a better understanding. So let me open the Verilog codes. So you can see how what is the hierarchy of the codes and everything. So then you can understand it better. So this is the Verilog HDL. You can see my screen, right? Hello.
Yes, sir.
Okay.
Very large screen is our
Yes.
smiling screen, sir.
Yes, yes. So this is our main module. So this digital PWM VMC is the main module that we are discussing. So we'll discuss the details, but I want you to understand. So first we are defining the input output declaration. Then we are discussing or defining the declaration of wire and register variables. Then we have defined PID controller gains. Then we have defined V reference and delta V reference. And then we have defined or we got the output voltage from ADC, and then we are generating error voltage. After this, these three lines are instantiating. So if you see, let me use this pen. So here we are calling another Verilog function clock generator, another digital PID controller, and DPWM dead time circuit. So we within the main module we are calling another three submodules. Like if you consider ripple carry adder, where we are calling full adder, which is submodule of ripple carry adder. Here also our main Verilog voltage mode control has clock generator, PID controller as well as DPWM dead time circuit. And then if you scroll down, then SAR is creating the transient events for load transient as well as referent transient, and then the module is ended. So before we go into these submodules, first we'll discuss the main module. So main module has different declarations and different submodules. So I just want you to imagine how the main module is written or what main module consists of. So first we'll discuss the main module. So main module is DPWM VMC, right? So this is the DPWM VMC. So if I have to summarize, DP,
Hello.
yes,
Yeah. Actually, previous class you thought about concatenation, right?
yes,
Operator.
concatenation, huh?
This is concatenation is for adding bits or reducing the bits. You can do.
Yes, concatenation is maybe I'll use this space. Say I have a 2-bit binary 1 0, and I have B, say 2-bit binary 0 0. If I do concatenation operation, sorry, let me draw this. So concatenation is we are concatenating two variables or more than two variables, say A comma B. Then this means it is 4-bit binary 1 0 0 0. If I am concatenating A with A, then it is 4-bit binary 1 0 1 0. So we are just concatenating A with A. So A will come, 1 0 will come next to 1 0.
Okay. Actually, in SAS lecture, I
Yes.
found like they are reducing the bits.
No.
in PFC.
I'll come to that point. So
Okay.
you are
Okay.
talking about the digital voltage mode control where SAR has reduced the bits. So yes.
Exactly.
Yes. Yeah, I'll come to that point.
Okay.
So one thing I want you to understand is when I use these brackets, it is concatenation always. And when I am using this square brackets, it means I'm accessing uh, some bits in an array. So this is for an array operation. Say I have considered A to be 320. A is a 4-bit. Now if I say A4, so this say it has A4, A3, A2, A1. So it is a 4-bit number. So A4 means A4. Now if I say A4 to 3, so I'm accessing 4th bit as well as 3rd bit. So I should not say A4. So as the maximum or the most significant bit is represented as A3, it means A4. And if I say A3 to A2, I am accessing 2 bits, which is A3 as well as A2. So I am getting A4 as well as A3. So SAR has used this square bracket, which we'll discuss when we go into that Verilog module. But just remember, this is for concatenation and this is used for an array or any vector variable. So we'll come there. So our DPWM VMC has 3 submodules. One is the clock generator and the other one is digital PID and the other one is DPWM with Deadtime. So our DPWM VMC is nothing but this block. So this block is the DPWM VMC. Okay. So the main module. So this is the copy pasted code from that Verilog. So we can discuss here or we can have interaction among us and we can better understand the code. So what DPWM has multiple number of ports, clock ADC, clock DAC. Even the clock DAC is not used in voltage mode control. SAR has put it, but SAR is not using it. PWM high, PWM low, ADC data, DAC data, Q load, QLR trend. And these are all the ports. Now SAR is defining whether it is input or output, whether it is input scalar or output scalar, or it can be input vector. So as you can see, we are writing sign. Sign means it is signed. And by default, in the Verilog, it is 2's complement. So it is 2's complement. So the simulator thinks that it is in 2's complement and we only use 2's complement in the code. But the DAC might be offset binary. When we discuss that current mode control, there we'll discuss, but it is 2's complement and output is vector DAC data. Even though we are not using this DAC data in voltage mode control, SAR has put it, but SAR is not using that. This will be used in current mode control. So SAR has defined inputs as well as outputs, and then SAR has defined or declared wire and register variables. So we have learned that wire is continuously driven and register can store the value. So again, wire can be signed or wire can be unsigned, reg can be signed or reg can be unsigned. Accordingly, SAR has defined whatever variables that SAR is going to use. And out is the digital number of V out, NE is the digital number of V error, and con is the control voltage in digital, FPWM is the PWM or FSW. So FSW is nothing but FPWM. So the first part includes declaring all the variables and everything. Coming to the next part. So after declaring all the, so I can say this entire thing declaration. So after this, R has defined what are all the parameters or controller gains. So whatever controller gains that are designed, again, these are not some random number. So these are designed using pole zero cancellation or whatever methods that we have discussed for voltage mode control, digital VMC. So using those methods, SAR has designed this KPKIKD for this voltage mode control. And if you see what is the format, Q format of this? Hello.
3.6. Sorry, 4.6.
4.6. So this is 4.6 and KI is 1.9. And again, this is also Q4.6. And underscore works like a dot, but the simulator will ignore this. So simulator will think it is 001010000. But for our understanding, we are putting this so that I will know it is Q4.6 format. But the simulator will think it as a 10-bit signed binary number. So this is so before like we are still in the main module, we have not even called the other sub modules. So after the PID controller gains, SAR has defined the reference voltage command, which is the N reference nominal. So this is like V reference, and it is also in Q1.9 format. And then delta N ref. So for a reference transient, SAR is using V reference plus some delta V reference. So this is that delta V reference, and SAR will add this whenever there is a reference transient. Else only V reference will be there and it is subtracted. So since this is digital, N reference minus N out. But if there is a reference tangent, then SAR will add this delta N ref to this N ref, so that N ref, the reference voltage is incremented, which is again reference tangent. And after that, SAR has defined some N ref temp for storing these values, whether it is a reference tangent or not. So for that, SAR is using wire and reg. And so these are all the reference voltage commands. After this, SAR is taking the output voltage from ADC. So ADC, so the ADC that SAR has used, SAR is operating it at 25 megahertz frequency. Input is say V feedback and the output is vector and out. So we have seen that ADC has a latency of say 5 cycles or 6 cycles. I don't remember, maybe say 5 cycles or 6 cycles. It has this latency. So when you give the output or whenever it is taking the sample, after 5-6 cycles of FADC, it will give us the output. So in order to be fast, we have to give very high FADC. So SAR is using 25 megahertz FADC, but this will keep on updating voltage, right? But I want only one sample per cycle. One sample per cycle. So I only need one sample per cycle, but this ADC will give me continuous samples. So what I will do, even though the ADC is continuously updating, I will only take once per FPWM. So FPWM is F switching, right? So whenever I see a positive edge, then only I'll take that V feedback and then I'll store it in and out. So the ADC is keep on updating, but I will not take that value. I'll update this once in a cycle. So whenever it sees a rising edge in FPWM, then only we are updating and out. So we are updating once in a cycle. Okay. And then, yeah.
Yeah. Actually, FADC is 25 megahertz, right?
Yes.
And we are delay, and it has 5 to 6 cycles delay.
Yes.
Let's say like the time of ADC is 40 nanoseconds.
Okay.
And if we delay it by 6 cycles, means 240 nanoseconds. After 240 nanoseconds, we will get one sample, right?
Yes.
Okay. Means after 240 nanoseconds, we will get one sample, or like full like whole.
So here, this V0 is taken sample by ADC. After 40 nanosecond, we'll get an out, the digital number. So after 40 nanosecond, the digital equivalent of this analog voltage sample will be generated by the ADC, and the output
Okay.
will be ready at the output. And so we are operating 25 megahertz. No? So 25 megahertz is around 40 nanosecond.
Yeah.
So this is 240 nanosecond. So after this 240 nanosecond, anode is generated. Again, after another 40 second, it will take another V naught sample and it will be generated after 240 nanosecond, right? Anode one.
Oh, yeah,
So it will keep
so
on updating, but I will not take all those values. I will take that value which is available at the rising edge of FSW.
exactly. You are meant like once in a cycle means 240 nanoseconds, right?
No, like once in a cycle means, see, there are so many samples that it will
Yes,
take.
after 240 nanoseconds, we are
Yes,
taking.
yes, yes.
Yeah.
So whatever, I'll say there is a switching pulse here. So this V naught is available here, but whatever V naught I am getting, it is sampled before 240 nanoseconds.
Yes, exactly.
Okay, yeah. So you may consider this as tau d, and the tau d that we are getting from the data sheet of ADC
is 240.
Yeah, yeah.
Yeah, thank you.
Okay. So then SAR is getting the digital equivalent of the voltage, the feedback voltage, and then using this assign statement, SAR is getting the error voltage, which is n reference minus n out. So after
Actually, can you elaborate N out statement? Like ADC data is 10 bits. Here we are taking only 9 bits, right?
Yes, yes.
And we are concatenation with one
Last bit to be 0. Yeah. So
Why they are
as if we are only utilizing 9 bits. We are not considering the 10th bit. So the reason is whenever we are implementing voltage mode control, the resolution of DPWM should be more than the resolution of ADC. Okay. So else what will happen? Else there will be something called limit cycle oscillations. So the details of this SAR has not discussed. It is there in that book that SAR has referred while discussing that this topic. So our ADC is 9-bit, right? So our ADC is 9-bit. Sorry, our DPWM is 9-bit. And I cannot use 10-bit ADC. So that's why SAR is using only 9-bit, and last bit SAR is always putting 0, as if only the 9 bits we are utilizing. Understood? So that we are making it equal. So else there will be limit cycle oscillation. So the details are there in that Luca Corradini book that SAR has mentioned, and you may refer to that, but keep this in mind. There is less than a minute. So if this meeting ends, quickly join in the same link so that we can continue. So after defining all these reference voltage and commands, SAR is instantiating 3 submodules. What are those submodules? The submodules are clock generator and a digital PID controller. Just a minute. So let me erase this. I'll use a different color. So one is the clock generator, and the other one is the digital PID controller, and the other one is the DPWM dead-time circuit. And these are again the inputs and outputs. So we are calling, or we are using the external signal by names. So if you see dot F clock of clock, dot F ADC clock of clock ADC, dot F DAC clock of clock ADC. This we have discussed in the last week, how to write this, what. So we are instantiating 3 modules. So these are the 3 modules. So let me go back to the screen. So first we have declared all the parameters, wires and registers that we are going to use. And we got the ADC DAC, and then we have instantiated these submodules that are inside this main module. But before we discuss these submodules, let us continue what is there in the main module. So below this instantiated modules, SAR has also defined the transient event. So we'll discuss that first, then we'll go to the submodules. So just keep in mind that we have clock generator submodule, digital PID controller submodule, DPWM dead time circuit submodule, but I'll come to this point after completing the main module. So we are still in the main module. So after instantiating the submodule, SAR has created transient events. So ntran is 100. So 100 cycles of TSW. So SAR is considering 100 switching cycles for transient. 100 switching cycles. And every time we generate another, so how the transient is happening, we have discussed that there is this switch with that switch register. So this is R continuous, R switching. So we have to generate this Qtran, right? So whenever this transient is 1, then it becomes shorted and R switch W will come in parallel with RC. The effective resistance will be low, so current will be high. And whenever it is open, then the current will be low. So in order to generate this, every time if we are getting a switching clock, we use a counter. So SAR has named it counter 1 and some reg Qtran and wire Qtran type. So Qtran type is QLR tran. So load resistance, load L stands for load transient, R stands for reference transient. So depending upon whether it is 0 or 1, the code will know whether it is load transient or reference transient. So then SAR is using this counter and ntran by 2. So for ntran by 2, qtran is 0, and for the rest of the time, qtran is 1. So accordingly, SAR is generating qtran for some amount of time 1 and some amount of time it is 0, but it is again user choice. Say your transient is happening very quickly, then you can reduce the cycles and make it a faster transient. So we are giving a square pulse to this switch, so that this is high load. Whenever it is 1, it is high load, and whenever it is low, it is light load. So we are basically writing a code so that I'll get this kind of switching pulse. And I recommend you to first understand the logic and write the code by yourself, and then only refer this, like if you get time. Because when you directly get into this, you are trying to understand the code directly without thinking, because this is not the only way to write the code. You might be writing in your own way and it will still work, because the logic should be same, right? The code can be different, there might be slight changes, but the logic should be the same. So you can write the code in multiple ways, and this is the way SAR is writing, but you need not actually copy paste the same code. If you want to use, you can use this code, but don't think that this is the only code. You can vary it slightly, and you can still able to get the same logic. So SAR is then getting this Qtran that will be given to this switch connected in series with the resistor. And then SAR is assigning a variable Q load, Qtran type. So if like SAR is checking whether Qtran type is 0 or 1. If Qtran type is 0, Q load will be 0. If Qtran type is 1, then Q load will be Qtran. So accordingly, SAR is getting this Q load and nref. So Qtran type, what is Qtran type? So Qtran type is QLR tran. So this is the switch which defines. So if it is 1, then it is load transient. If it is 0, then it is reference transient. So accordingly, SAR has written the logic. Again, you don't have to exactly follow this logic. The logic is same, then code can be different. Whatever way you are comfortable to write, you can write in that way, and until and unless that logic is implemented. So SAR is using this logic, but you are free to write your own logic and still able to achieve this. Yeah.
Hello.
Yeah.
Yeah, in first always passage that para that
Yeah.
here nref temp one variable is there.
Yes.
What is that?
So nref temp is this nref temp.
Okay.
So whenever SAR is creating load transient, n reference temp is the n reference. Means SAR is using n reference nominal and not n reference nominal plus delta n ref, which means the load, the reference transient is not happening. So here, if you see, SAR is using n reference nominal, which is V reference, and delta n ref, which is for delta V reference. So SAR is not using that. And this is load transient, so SAR is not changing that. But if you want like say reference transient, then SAR will change it accordingly.
Okay. This is a register, right?
Yes, register.
Okay.
So that's what I'm saying. Like the logic is whether you want load register, load transient, or reference transient, and accordingly SAR has written the code. You just have to understand the logic, not the line to line exact code that you have to follow. This is a way that SAR has written the code, but it is not mandatory that you have to write the code in this way. There can be multiple ways of writing the code, and this is the way that you can refer to if you are facing any difficulty. But just think about it that you need some load transient, you need some reference transient. So what are the inputs and what are the outputs? What is the logic in which you can write the code? Just think about it, try to write and see whether it is working or not. And if you face difficulty, then you can refer to this code. Directly, if you look at this code, then you will not think, right? So this will hinder your thinking power, but you can always follow this code. As this code is tested and it is working fine, you can always refer to this code. But this is the logic of the main module. So now we have discussed everything. So load transient, reference transient, everything is done in the main module. So before we go into the submodules, I just want to show you. So this is the main module, and if you click this plus, these are the submodules. One is the clock generator, other one is the digital PID controller, the third one is the digital PWM deadtime circuit. So first we'll discuss about the clock generator. So clock generator. So clock generator, if I assume it as a block, it has FSW, the 100 megahertz, sorry, F clock. 100 megahertz clock, which is F clock that SAR has named it, and the output are FADC, which is needed for voltage mode control, FDAC, which will be used for current mode control, and FSW. So SAR has used ADC clock, so both are the same, and DAC clock. This is also DAC, and FSW is FSW. And F clock is the main clock. So main clock is the input. So SAR has defined the main clock as main clock. And this is this. And the output SAR is defining as reg. Now I have a question. So the main clock is F clock is 100 megahertz. And FSW is 200 kilohertz, the frequency at which the buck converter is being operated. And FADC, which is equal to again FDAC, is 25 megahertz. So we are using a counter. So what should be the value of counter until which it should count, so that I'll get FSW 200 kilohertz? Can anyone tell me what is the logic? Say NSW. I am using a counter, right? So what is the value from 0 to that NSW minus 1 or NSW that I should count, so that I'll get F clock to be like this? Or so that SAR got one switching frequency, TSW. So the logic is simple. Each step size is T clock, right? So T clock into that overall thing is, say, NSW plus 1. Because it is 0 to NSW, NSW plus 1 will give us T switching frequency. Now, if you write 1 by F clock and this one by FSW, you will get F clock is equal to NSW plus 1 into FSW. So I will get NSW plus 1 is equal to F clock 100 megahertz by 200 kilo. So this is 500. So my NSW is 499. So I have to count till 499 so that I'll get 200 kilohertz clock from 100 megahertz. Similarly, if I use another color for NADC, I'll get NADC plus 1 is equal to 100 megahertz by FADC, which is 25 megahertz, which is 4. So my NADC should be 3. So that's why SAR is using NSW 499. and NADC 3. So SAR is using one counter for NSW or FSW and the other counter for FADC. So initially SAR has made both of them 0, and then SAR is using again always at the rate POSH clock one code for switching frequency, generating switching frequency. So this is again a counter based. So we are counting it and we are resetting it whenever the counter reaches this, and otherwise we are incrementing the counter. So this is the logic that we had discussed last week, so I'm not going into the details. So one is for switching frequency and the other one is for ADC DSC clock. So we have one question in the chat box. 8. Shankar, what do you mean by 8? Okay, just explain me, or if it is a mistake, then it is fine. So the clock generator, we have got FSW using one counter based always block, and the other part is the ADC and DSC clock. So ADC DSC clock, now here it will count until an ADC, so it will count till 3, so that FADC will be equal to FDAC will be equal to 25 megahertz. So here we have used same switching frequency for both of them, but you are free to use different clock frequency for both of them. So depending upon that, the speed will vary. But for simplicity, we are using the same clock frequency so that it will be uniform. So this is the clock generator. So this is the end of clock generator. So let me go back here. So first we have defined the input and output, then we have defined the parameters that are needed to generate that switching clock, and then we have defined the registers for counter. So the first always block gave me the switching frequency clock, and the second always clock gave me the ADC and DAC clock. So that ends the module clock generator. Okay. Now, coming to the digital PID, we have already discussed what is the digital PID controller structure. So this is the structure that we had discussed in that particular week, where we have discussed about the forward difference, backward difference, and we are using the backward difference. Now, what is VC of n? So let me change the color. So my VC of n is, say, UP of n plus UI of n plus UD of n. So one is proportional, one is integral, one is derivative. And UP of n is nothing but Kp into V error of n, multiplication. And UI of n is an iterative addition. So Ki star VE of n plus UI of n minus 1. So this is an iterative addition and it will keep on adding up. And Kd of n or UD of n is Kd into VE of n minus VE of n minus 1. So this is the logic. So we are going to write this code in Verilog. So how do we write? So before I go into the code, let me show what is there in the digital PID controller. So digital PID controller, again, we have defined input and output, all the wire and edge that we are going to use. And then we have started multiplying Kp into an error, all those things for proportional, for integral, as well as derivative. So I'll come into this when we go into the PPT. And then finally, we have added all and prop and integral and derivative. So that is the outline of the code. So now we'll go into the details. So digital PID. So this is the module name, digital PID controller, and these are the inputs and outputs. So what is the input? V error. So NER is the error, digital error, that is the input, and FPWM. Why do we need FPWM? We have to synchronize with the switching clock, right? So that's why we need FPWM. So this Z inverse will update once in a cycle, right? So it should be updated with the new UI of n, which is once in a cycle with respect to this FPWM. And then ncon is the output, and Kp, Ki, Kd are the parameters that we are going to use. So again, sir has defined input and output. So from here till here. So these are all declaration of, so these are all declaration of inputs, comma, outputs, comma, whatever the wires that are needed and whatever the registers that are needed for our code, all those are being declared. And from here to here, the code starts. So n prop temp. So some temporary variable that SAR has used. Why SAR is using that will come. So what is n KP that SAR has used? KP is 4.6 and n error is 1.9. So if you multiply, you will get 5.15, 5.15, and we have discussed there are two sign bits and one we have to remove because we don't need two sign bits. So it will be Q4.15. Similarly, KI is 1.9. Hello, can you hear me? Hello.
Yes, sir.
Okay.
Yes, yes.
Okay. And Q is again 1.9. So it will be 2.18. 2.18. But again, it has two sign bits. So it will be Q1.18. So whatever SAR is doing this operation KP into V error and KI into V error. So this part SAR has done. So this is 4.15. This is 1.18. Next, what is SAR doing? SAR is doing the derivative part. So derivative part, what SAR is supposed to do? SAR is supposed to do VE of n minus V error previous, right? Into multiplied by KD. So now if you come here, these are what? Blocking statements. Hello. These are blocking statements. So what do we mean by blocking statements? First, this will be simulated or this will be implemented and then this will be implemented. So what we are doing NDR temp is KD star n error minus n error previous. And now I'm updating n error previous with n error. So what I'm doing is first I'm considering n error minus n error previous. Then I am updating n error previous with n error. So first this will happen, next this will happen. So that's why I'm using blocking statements. Whereas if I put less than or equal to, which is the non-blocking statement, then n error previous will be updated with the an error and this will also be happening at the same time, which I don't want. First I want this to happen, after that I have to update the an error previous. So that's why I'm using blocking statement. So that's why we had discussed about blocking statements. Again, KD star an error, say KD star an error. So it is Q4.6 star Q. KD is also Q4.6. So 1.9. Again, it is 5.15, which have two sign bits. So it is 4.15. But what happens is whenever we are multiplying, say 10 bit with 10 bit, this will be 20 bit. This will be 20 bit because we are multiplying two 10 bit numbers, because we know that there is one redundant extra sign bit which we should ignore, but the simulator does not know. So it will give 20 bit here, and here also 20 bit. So here also we will get 20 bit as we are multiplying 2 10 bit. But we know that it should not be 20 bit. In fact, it should be 19 bit because there is one redundant sign bit. So what we are doing, so what is n prop temp? N prop temp is 20 bit, which means 19 to 0, right? So there are 20 bits and the representation is 19 to 0 and the most significant bit is redundant. So MSB is redundant. We don't want, and which it is not needed also. So we have to ignore the most significant bit. So SAR is using this operation. So it is n prop temp 18 to 0. So SAR is considering the 19 bits excluding the most significant bit. So this is Q4.15, which we are told here, and this is 1.18. 1.18 and NDR temp also we got 20 bit and the most significant bit is redundant. So we need Q4.15, Q4.15. Fine. So now n we know that ui of n is ki star ve of n plus ui of n minus 1. So similar to KD, say what we are doing, KD, we are multiplying an error minus n error previous, and then we are updating n error previous with n error. Similarly, in integral, first we'll do this, and then we'll update ui of n minus 1 with ui of n, right? So first, whatever ui of n minus 1 in this cycle, or whatever ui of n in this cycle will be ui of n minus 1 in the next cycle. So after performing this statement or this expression, I should update this ui of n minus 1 with the ui of n. Again, first I have to do this, then only I have to do this, which means again I have to use blocking statement. So again, these are blocking statements. So if I map one on one, so n int temp2 is my this one. So this is ki into ve of n, plus there is some other expression which is n int temp3, which is ui of n minus 1, which is ui of n minus 1, which is ui of n minus 1. So n int temp3 is nothing but ui of n minus 1. And then let me use some different color, maybe black. N int temp4 is ui of n, which is also here ui of n. So we are doing the same thing which we had done for derivative. First we are doing this, we are implementing this, and then only we are updating our ui of n minus 1 with ui of n, which will be used in the upcoming or the next iteration. So this updated ui of n will be used as ui of n, and it will keep on adding. So this is the one-to-one mapping of these variables with this. So now our ui of n is n int temp4, and we have n prop 19-bit as well as n der, which is also 19-bit. So now what is needed? Now we have to accordingly add them. But before we add them, so SAR is doing what we had discussed. N prop, n int, n derivative. Now let me change the color. This is Q4.15. This is Q1.18. This is Q4.15. When there are two different Q formats, then the summation will be maximum of m dot maximum of n. But before we add, we have to make sure the Q format is same. So what is SAR doing? SAR is changing this Q1.18 to another format, which is Q4.15. So how SAR is doing? So .18 has become .15, which means SAR is removing the least significant bits. So this is that least significant bits. So this is responsible for .15. Instead of 18 to 0, SAR is considering 18 to 3. So SAR has neglected 2, SAR has neglected 1, SAR has neglected 0, which means SAR has not considering the 3 bits at the end, which makes it .15. And how do I get 4? We had discussed when we are increasing the MSB, we had to pad with the most significant bit. So this is the most significant bit 1, this is the 2, and this is the 3. So we have added 3 additional bits to this one, which makes it 4. And we had to add the most significant bit, which is n int temp4, and it is 4.18. You understood, right? This like expression is very crucial. If you had not understood, I'll explain it again. Did you understand this? How we are changing the Q format?
Sir, this last thing 18 n in temp4 18 is to 3. That is
Yes.
understood, sir.
Okay.
We are removing the last 3 bits. But how to add this? How to convert this 1 into 4?
Okay. So let me come back here. So first we are doing Q1.18 to Q1.15. Now, how do I change it 1.15 to 4.15? I have to pad the most significant bits 3
Yeah,
times.
we have to add 1.
Yeah,
Yeah.
so it is not
Okay.
always 1. If it is 0, I have to add 0. If it is 1, I have to add 1. So most significant bit, whatever the most significant bit, I have to add or pad it 3 times. So I'm considering n into temp4 18, which is the most significant bit, 1 time, 2 time, 3 time, comma, the other 15 bits. So now
Okay.
Q1.15 is become Q4.15. So this is an
Okay.
instantaneous. Now all 3 of them are in the same format, I can add them together because the Q format is same. And this is to put the saturation. So this is the saturation. Because integral is keep on adding it. What happens, say we have n number of bit, say 0, 1, 1, 1, 1, 1, 1. Now it is a positive number. If I add 1, it becomes 1, 0, 0, 0, 0, which is a negative number. So integral is converting from the most positive number to most negative number, which we do not want. Or say for protection purpose also, we put a saturation limit so that that integral will not cross beyond some value for protection. So for that purpose, SAR is using this block, which is the saturation. And this is for again protection purpose. So now SAR is using, SAR is adding n con is equal to n prop plus n int plus n derivative. So this expression or this line is nothing but this line. Where is the mouse? So that line is nothing but this line. So sorry, got UP of n, UI of n, UD of n, and then SAR is adding at the end. So this completes the PID controller. So just to summarize, we had this module. Initially, we have declared input output and all the wires and registers that are needed. And then we did n prop, n int, and derivative. And then we have changed the Q format so that it can be added. Also, so this is the changing the Q format so that we can add all three of them. Then we have put some saturation on and it so that it will act like a protection. And then we have added. So this completes the PID controller. Coming to the DPWM. So DPWM part is exactly same as whatever we had discussed last week. So let me write this. So this is discussed in week 7. So that's why I'm not going into the details of this because we had to discuss current mode control as well. So this is exactly the same code that we had discussed last week. So this is the counter based DPWM, and this is the code. So let me show it here. So counter based DPWM, again we have input output, all the wires and registers that are needed, and a counter and the control output. So using that control output and counter, we are getting this. So it is like this, right? So the counter is, this is the counter, and on top of the counter we have this control voltage. Now this will generating the duty ratio pulse. So this logic has been implemented in this code, which we had discussed last week. So this gives us QPWM. Now using this QPWM, I have to get QH comma QL with the dead time. So that dead time logic also we had discussed by keeping multiple D flip-flops in series. So which will give like a delay. So we have considered, I think how many? 1, 2, 3, 4, 5, 6. So we have 6 cycles of clock. So 6, 10 nanosecond. So we have 60 nanosecond delay. And then we had also discussed how this logic is coming from their timing diagrams. So this logic is this logic. So we had discussed all these things in the last week. So I'm not going to discuss this again. So this completes our digital voltage mode control Verilog HDL. And for the hardware results, SAR has considered these power stage details. This inductance capacitor, we reference switching frequency 20 kilohertz, and this is the RC and RSW. And these are all the controller gains that SAR has designed for this power stage using the controller design methods that were discussed in the earlier weeks. And then ADC resolution is 10 bit, but we are removing 1 bit on purpose. So it is becoming 9 bit. So that DPWM resolution will be equal to this. And the clock frequency is 100 megahertz. And the V feedback gain that we had discussed is 0.27. And VM is the ramp voltage. So the ramp voltage is from 0 volt to 2 volt. So these are the controller, these are the controller details. So these are the gains, or these are the parameters, these are the values that are considered for the hardware implementation of this voltage mode controller buck converter. And quickly going through the load step up transient and load step down transient. So this is the load step up transient, you can say this step up transient, and the delta V naught is 180 millivolt. So this delta V is 180 millivolt, and the settling time is 100 microsecond. And for step down transient, it is also 180 millivolt. And TS is 80 microsecond. Again, SAR has done the reference transient. So whatever code that SAR has used for reference transient or load transient, that has been implemented. And for we got the reference transient. I think SAR is going from 1 volt to 1.1 volt here, and here 1.1 volt to 1 volt back. But SAR is using here RC. So the continuous resistance has been used. So the current is at light load. Now coming to the mixed signal current mode control. So till now we have discussed voltage mode control. So voltage mode control has three sub blocks: digital PID, clock generator, as well as the DPWM. So in mixed signal current mode control, there are two loops, as we know. One is the digital loop, and the other one is the analog loop. So in digital loop, what is the digital loop? In digital loop, we have voltage. So there are two loop. It is a two loop control. Voltage is in the digital domain and current is in the analog domain. So that we are going to discuss now. Sorry. So first, again, we'll discuss the design methodology, the top-down design, and then we'll go into the Verilog HDL implementation, and then we'll see some hardware results. So everything is same, except there are a few additional blocks because there are two loops. So this is the basic mixed signal current mode control architecture in buck converter. As we have discussed, there is this R1, R2 to make sure that this feedback lies within the range of V span. And here we have PI controller. And this is one additional block. We'll come to this point. What is current reference? Why it is needed? And then digital to analog converter. So digital to analog converter also has some output span, right? So whatever the range of value that VP has, the similar range of value V sense should also have. So whatever current sense resistor that we are using here, it has a gain, right? We have discussed there is some gain for current sense amplifier, say KC, which is the gain of sensing that we have discussed last week. There is a gain for current sensing, so that KC multiplied by IL is this V sense voltage, which is compared with the control voltage, giving us the reset pulse and then set pulse. So again, this part is in analog, so that's why this is out of the digital controller. So this part is in analog because this is the current loop, and the other part, rest part, is the voltage loop. It is in digital. So everything is similar to voltage mode control, except voltage mode control is directly giving PWM high, PWM low, whereas here this is giving DAC data, which is going to digital to analog converter. So we need FDAC as well as FADC. And one thing you should keep in mind, that ADC data is 10 bit and DAC data is 12 bit. Now this is being compared with the IL, which is giving the Q comp, and using this Q comp, which will again act as the input. So this Q comp is the reset pulse. Why? Because this is the Q comp. Right, Q comp is the output of the comparator. So output of the comparator is the Q comp or the reset pulse that we are discussing about. And then it is again also the input to this Verilog module. So this is our main module. Okay, so these are the inputs and these are the outputs. So before we go into the code, let me just quickly show the Verilog code, which is mixed signal current mode control. We have this. You are following, right? Hello.
Yes, sir. Yes, sir.
Okay. So first I'll show the hierarchy of the code, what is there inside it, and then we can discuss. So this is the main module. If I click this, it has sub modules: clock generator, digital PI controller, current reference, PWM deadtime circuit. So again, whatever that is followed in voltage mode control, same thing. First, whatever inputs it has, we have to define the input output port declaration, and whatever reg and wire that we are going to use, same thing. And then KP, KI, KD. In this case, KD is not used, but we are not using KD in the controller, but the value is remains same, and KP, KI are being used. And one thing we have to remind ourselves, KPK, whatever values that are used in current mode control are not the KPK values that are used in voltage mode control, because those two are different control techniques. We have to design KPK, and accordingly you have to use the KPK. So whatever KPK that are used in current mode control and whatever KPK that are used in voltage mode control, they are not same. We have to design for both the architectures using the methods that we had discussed in the earlier weeks, and then we have to get the KP value, and then we have to convert this in this Q format, and then accordingly we write the code. Then again, same thing, reference voltage commands, V reference, delta V reference, same as voltage mode control. Then we are getting the data from ADC and generating the error voltage. So this is the error voltage command. Then these are the sub modules. So we have how many sub modules? Clock generator. Again, clock generator is same as voltage mode control. Digital PI controller. Instead of PID, we have PI. So there is no derivative part. You have to just exclude or remove all the derivative part code lines, and you have to write implement only PI. And then current reference, this is the new, and PI deadtime circuit, this is also somewhat new. So this is not DPWM, it is PWM deadtime circuit. So this block and this block are the two. Let me change color. Let me use a different color. So we have current reference and PWM circuit. So these are the additional two new blocks. And these are same as voltage mode control. That's why I'll not be going into this again, because these are the same. So we have a code question, sir, which software to write VHDL program? So this is Venkatesh. So this is Verilog ISC, Xilinx ISC. So this is Xilinx ISE software. So the details of which I have mentioned in week 6. There is less than a minute. If this meeting ends, quickly join so that we can continue our discussion. So in week 6 PPT of mine, I have shared the link in the last slide or last slides, where you can access the link, YouTube link, and then you can install this software. Okay, sir. Okay. So this is the instantiation, and then transient events, everything is same as voltage mode control. So all these are as in the voltage mode control, just copy paste. Only these two submodules are additional, which we are going to discuss. Other parts I will not discuss, as they're discussed in voltage mode control. Is that clear till this point?
Yes, sir.
Okay. So I think this meeting will end. Quickly join, then we can start discussing the these two submodules. So we are going to discuss only these two submodules. So just to summarize, so the architecture is as follows. The output voltage using a gain 0.27 is converted into V feedback voltage, which is fed to analog to digital converter. The output is an out subtracted from N reference, giving an E error voltage, fed to PI controller, giving the control voltage. And this is the new block, current reference block, which we'll discuss in the next slide, giving rise to the control voltage, or say NP, whatever the naming is, NP. It is fed back to digital to analog converter. The output of which is fed to this comparator. So this is the comparator. And what is the other input to the comparator, which is the scaled version of IL. So this KC is the gain of the current sense amplifier. It is 0.01 volt per ampere. Because we are converting some ampere current into an equivalent voltage. So that's why the unit is volt to ampere. So the input is ampere and output is volt. So this is the equivalent voltage. This is also equivalent voltage. So that's why we can compare. And the output is Q comp reset pulse. Again, only this part is the analog part. Rest of the part is in digital. And this is fixed frequency. So this is the set pulse and dead time, PWM high, PWM low. So this is the main module as we had discussed. Yeah.
So in that previous module, previous slide,
Yeah.
sir, why the DAC is taken to be of higher resolution than ADC here, sir?
Yeah. That is a good question. Thanks for pointing out. So in voltage mode control, in current mode control. So in voltage mode control, say we are talking about resolution. So here we say DPWM resolution should be more than ADC resolution or equal to, and here DAC resolution should be more than ADC resolution. So what happens if this does not like if it is not followed? It might lead to something called limit cycle oscillations. Limit cycle oscillations. So the details of which are mentioned in that Luca Corradini book, Digital Control Luca Corradini book. So Sir has mentioned the name of the book in the earlier lecture video, so you can
Yeah,
go
we
to
got this lecture.
yes. So the reason for which is mentioned in this, which we are not discussing in the course, but we are letting you know that this has to be obeyed, else this might lead to limit cycle oscillation. That's why we are considering the DAC to be 12-bit and ADC to be 10-bit, and it can be like this can be 8-bit and this can be 10-bit also. So it has to be more. As we have considered high resolution ADC 10-bit, we are considering DAC to be 12-bit. Now the main module is as follows. So here there is a code input output declaration, register declaration, KPK parameter declaration, everything, and module instantiation, and then followed by the load transient code, reference transient code, which is same as this. Everything is same as voltage mode control code. So that's why we are not discussing them again. And this is also same as voltage mode control. And clock generator digital PID controller, these are also same as voltage mode control. The code is just copy paste, but except here we have PI. So you can say ncon. Ncon is UP of n plus UI of n, and whereas UP of n here UP of n is nothing but KP star into V error of n. So it is just the copy paste code of PID controller, and you have to just delete all the derivative code lines, and it is PID controller. So this is a subpart of PID controller, and it is a copy paste code. So that's why we are not discussing this. And what we will be discussing are these two modules, which are new modules, which are not there in voltage mode control. So we'll go into this. So before going into current reference, I just want to show how the code is there. So these are the submodules, current reference. So current reference again, it is same as other modules, input output declaration, parameter declaration, and then the code will start, and something is happening here, which we'll discuss. And the output is I reference. So this is the code part. These are the declaration part, and this is some parameters that are defined. So we'll discuss what this why this code is written and what is the use of the code. So the current reference is this block which we are talking about. So the input is the control voltage. So why are we not giving the control voltage to directly DAC? Why we are putting the current reference, and why then only we are giving it to DAC? So there are two reasons for this before we go into the code. So ncon is in what? 2's complement, right? And this is in what? Offset binary. So what we have to do? We have to toggle the most significant bit. So how do you convert this? You should toggle or invert the most significant bit. This is one reason why we need current reference, so that we will match the binary representation. The other thing is, as this is a current mode control, it needs safety, right? So we can put a saturation block like this. So the current, if it crosses, it will be saturated at N max and it will be saturated at N min. So this is, you can say, N con. So we are putting the N-con saturation limits because it is current mode control. Inductor, all the switches might have some current requirements, and even during transient or any situation, we don't want current to cross certain limits. So we will put the saturation limit, which will act like a protection or any other purpose. So for these two reasons, so these are the two reasons why we need the current reference block. So what we are actually doing is we are changing the representation from 2's complement to offset binary. Also, we are providing the protection. So ncon, all these things up to this line are declaration, which I don't want to explain. They're self-explanatory. And these are the protection, maximum as well as a minimum. So maximum is positive, right? So most significant bits are 0. Minimum is negative, so most significant bits are 1. So as the most significant bit is 1, it is the negative number. So one is negative, other one is positive. Although we are not using negative because our current is always positive, we are not using this n min, we are only using n max. But if your current goes negative also, then you can use this. So okay, let us come back here. Ncon nominal. So what is Ncon nominal? Ncon nominal is Ncon 18:4. Again, what is Ncon? Ncon is 19 bit, right? 19 bit. And digital to analog converter is 12 bit. So what is the Q format of this? Q format of this is Q4.15. And so what SAR is doing? SAR is neglecting the last 4 bits, which is 3210. So what it becomes? It becomes Q4.11. Why the Q format of this is Q1.11? So we need only 11 bits after the dot. So that's why SAR is neglecting or removing the least significant bits. And after that, SAR is these two are again redundant, so these are not used. And this is Ncon nominal greater than N max, then we are making it N max. Say our Ncon nominal is here, then we are checking if it is more than Ncon nominal, we are putting N max only. So that is the N max. Else, so if it is more, then we are restricting it to N max, which we are saturating at N max. Else, this again has to be converted to which format? Q1.11, right? So Q1.11. So out of these 4 bits, we'll consider 1 bit, which is the MSB, most significant bit, padded by the last 11 bits. So this is the most significant bit, 14th bit, padded by the last 11 bits. So what we are doing, we are checking if Ncon is more than Nmax, then we are considering Ncon is equal to Nmax, and we are writing it in Q1.11 format. Else, our Ncon is same as Ncon, and again we are writing in Q1.11 format. But whatever we, so now we have matched the format, but it is still in which format? 2's complement. But how do I change it to offset binary? We have to toggle the first bit. So that is what we are doing here. So we are toggling the first bit. So inverting the first bit. Now this becomes Q1.11 offset binary. Why offset binary? Because the DAG that we had selected or we had been using, it is offset binary. So the DAG decides the binary representation. So first we are declaring it, and for protection purpose, we are deciding Nmax. And then from 4.15 to we are converting 4.11. Then 4.11, I'm putting that saturation limit. If it is more than that, I am restricting it to Nmax that I had defined here. And that 4.11, I'm converting it to 1.11 because DAC is 12-bit in Q1.11 format. And then it is in 2's complement. Now I'm inverting the most significant bit so that it becomes offset binary. I hope this part is clear. Is this clear? Current reference part.
Yes, sir.
Okay. So this is one new module, which is the current reference. Now the other current reference is PWM dead-time circuit. So let us get back to PWM dead-time circuit. So PWM dead-time circuit is QComp and FSW. So this part, okay, let me pull this down. So this part is the PWM
Sir,
dead-time. Yeah.
sir, here, this DAC, the DAC accepts the binary format, no? That
Yes, yes.
so, sir, offset binary format it accepts.
Mhm.
But here that ncon is in 2's complement form.
Yes.
Sir, we are converting to offset binary just because this DAC understands
Offset binary.
only this offset binary.
Yes.
So suppose here we are having suppose this ncon in 2's complement form. If it is in suppose it has some minus 1 amps is represented in that form
Okay.
in the digital form.
Yeah.
So the toggle form of 2's complement form will be the MSB will be toggled.
Yes.
So this DAC, the toggle to form, this DAC understands as minus 1 amps.
Yes. Yes.
Okay.
So the
So
DAC
it is
that we are
because it is
using.
DAC.
Mhm.
Okay.
If
So
the
why
DAC
we are
is
actually going into this?
so
What is
like
the
continue.
this offset? Why there is a requirement of offset binary, sir? Because this DAC, why it is coming to know only that binary offset binary form.
Okay. So for our requirement, we had selected a very high frequency 12-bit DAC for our requirement, and depending upon their ease, they are using 2's complement. Whatever the DAC that they had already made, it is 2's complement. So we had to give the input to the DAC as 2's complement. So why they had chosen 2's complement, it is up to their requirement. Maybe they had gotten some advantage in terms of architecture or the number of cost. Maybe they are going for 2's complement, but we do not know the reason why they had gone for 2's complement. But as we had selected the 2's complement DAC, we have to give the input 2's complement. That's why we are converting. Had it been sorry, offset binary, I'm sorry, so it is offset binary.
Yeah, offset binary.
Offset
Okay.
binary. So that's why they are using offset binary, not 2's complement. Whereas the ADC, they are using 2's complement because they had made the 2's complement ADC, and it can also be offset binary. There is a provision. You have to connect the circuit in such a way so that you can access 2's complement also, and offset binary also. But DAC, they are making offset binary, only offset binary, so that's why we had to give offset binary. Had it been only 2's complement, then we had to only put saturation limit, match the Q format, and send it as it is. But because it is offset binary, we have to go offset binary. So one student is asking, sir, PWM saturation present after that time? No, there is no PWM saturation. We are saturating the current which is before this dead time circuit. So the saturation block is present only in this current reference. So this is the saturation. We are saturating the current for protection purpose. Now coming to the dead time circuit. So dead time circuit has one clock, main clock, FPWM. This is FSW, comparator output, and output is QH and QL. So first we will generate this QPWM, which will go into the dead time circuit. Again, SAR is declaring the input, output, wire, and reg that are needed for the code. And then so SAR is using one variable reset, which is comp out. So reset is the reset pulse, and FSW is the set pulse. So the code is as follows. Either at the positive edge of FPWM, so I can say this is the PWM or FSW for our ease of understanding. And the other one is the reset pulse. So this is the reset pulse. So now we are drawing the timing diagram. So always at the rate positive edge FFPWM. So now it enters the code. So it enters the code. Begin if reset. If reset means if reset is 1. Is reset 1? No, reset is 0. So else if FPWM. So FPWM. So is it FPWM means FSW is 1 or not? Yes. So QPWM is set to 1. Is set to 1. So up to what point is it set to 1? Up to that point, it again enters this function. So it will enter the function. Now, until it sees another positive edge on FPWM or another positive edge on reset, it will be 1. So until this point, it remains 1. So now it has seen the positive edge reset. So it enters the code. If reset. If reset means if reset is 1. Yes, reset is 1. QPWM is 0. So QPWM is set to 0. So until what point is it set to 0? Until it sees another rising edge on PWM or reset. There is another rising edge on PWM here. So again, it is set here 1 and here it is set 0. Yeah.
Sir, here this non-blocking is used in here.
Yes,
QPWM.
non-blocking. Yes.
Sir, non-blocking is, we said it is parallel assignment.
Yes.
Blocking means it is sequential.
Yes.
Sir, here if QPWM is assigned 0, since it is parallel,
Okay.
since it
Understood.
is a non-blocking statement. Okay.
So when we say blocking and non-blocking, they should be inside within a particular module. But if I say if, say x1, some statements, else if x2, some statements. If the blocking and non-blocking are within this module, then they will happen at a time. And if they're within this module, then they'll happen at a time. But the module here, like the line here and the line here will not happen at a time, because it depends upon if x1 else if x2, because else if x2 will only be entered if x1 is false. If x1 is true, then it will not enter this else if. Similarly here, if reset, if it is reset, then it will enter this and done, it will come out of the loop. But if reset is 0, then this will not happen, and then it will check if PWM is there, then it will enter and PWM is 1. So at any given point of time, it will not enter both the pulse, I mean both the if conditions. It will enter any one of the if conditions, so any one of them will happen. Okay. So that is the logic. So like if you directly look at the code, you will not understand how it is working, but I recommend you to like draw these timing diagrams and see how this is happening. So is this part clear how we are getting? So now we got the QPWM, but so this is the QPWM. Now we have to again put the dead time circuit. So QPWM will be passed through this dead time circuit, which will give PWM high, PWM low. And the dead time circuit is same as voltage mode control and whatever we have discussed in the last week. 6 clock cycles with 10 nanosecond, which is the 60 nanosecond is the dead time. And this logic is giving us QH and QL. So let me come back quickly here. So this is the current reference that we had discussed and the dead time circuit. So initially we had declared input output ports, and then here using this always FPWM reset, we are getting the QPWM, and after that QPWM we have this dead time circuit, and this is the logic to get QH and QL. So this completes our current mode control Verilog HDL. Now coming to the hardware results, as you can see the KP and KI, these are different. They are different from the KP, KI, KD of voltage mode control,
Yes.
because they are different control techniques. The values will be different. Accordingly, they have been designed using the techniques that were discussed in the earlier weeks. And as we have discussed, Kc is the current sense gain. So from ampere to voltage, it is being converted. So it is, you can say, 10 millivolt per ampere. So if there is 1 ampere current flowing, it will generate equivalent 10 millivolt output voltage at the end of sensing. And ADC is 10 bit, this is 12 bit to not have limit cycle oscillations, else there will be limit cycle oscillations. KF is the voltage feedback gain 0.27 and clock frequency is 100 megahertz. Power stage remains, power stage details remain same as the voltage mode control. So coming to the hardware results, one is the load step up transient, and delta V naught is 175 millivolt, and settling time is 80 microsecond. Here also it is around 170 millivolt and 60 microsecond. And for reference transient, settling time is 50 microsecond in step up transient, and for step down transient, it is around 40 microsecond. So these are the results. I think Sir has already shown the live demonstration of these things. So you can go through
The
those
step up
videos.
transient means
Yes, reference step up transient means
steps.
yes.
No, the RC is added. No, the switch is closed.
Yeah, like there are two things. One is the load step up transient, other one is the reference step up transient. So for load step up transient, so what they're doing is they have this capacitor, and then they have this RC, and then they have this switch connected to RSW. So this is RC and this is RSW, and this is Q tran or Q load, whatever Sir is using. So at this instant, the Q load is turned on, and at this instant it is turned off. So if you draw the Q load will be something like this. So here it is 0, here it is 1, here it is 0. So this is the Q load. Similarly here, if I draw with another color, here it is 1, here it is becoming 0, here it is becoming 0 until this point. So this is the Q load. This is 0, sorry, this is 1, this is 0, this is 1. So whenever Q load is 1, current is high. Whenever Q load is 0, current is low. And
this is
reference
light load.
transient, yes, this is full load, this is light load.
Okay.
And for reference transients, R is directly giving 1 volt to 1.1 volt or 1.1 volt to 1 volt. So this we had already discussed in the code. It is the same logic. And yeah, this completes the voltage mode, voltage mode control and current mode control. Now coming to the pulse skipping modulation, PSM. So why we use this? We use this in light load condition. To reduce the losses. And this is a DCM operation. So current will touch 0 and it will remain at 0. So the waveform, you can say it is something like this. So ours is voltage based PSM. We'll quickly go through this. Majority of the part will be same as voltage mode control or current mode control. So first we'll discuss the top-down design methodology, followed by Verilog HDL, and followed by hardware results. So again, everything is same. We have this V feedback, gain is 0.27 going into ADC. So here the logic is, if the voltage is less than V reference, then we'll feed a fixed duty ratio pulse. If the voltage is more than V reference, then we'll skip. So we have two things. One is the charge pulse, and the other one is skip pulse. So charge pulse will happen if V naught is less than V reference. Skip pulse will happen if V naught is greater than V reference. So the inputs and outputs are as follows. Entire thing remains same as voltage mode control, because there is only a voltage loop, but only the logic is different. So here we have digital PSM block instead of voltage mode control. So inputs and outputs are same as voltage mode control. Only here, instead of changing the or generating the duty ratio, we are feeding either with duty ratio, or we are skipping the pulse. So this will decide, this D will decide 0 or 1. If it is 0, then this is 0. If it is 1, we'll get QPW. So the output will be either, so if I say 0 means skip pulse, QPWM means charge pulse. So this logic we have to implement in the Verilog HDL. So before we go into the code, let me quickly show. So let me quickly show the code, Verilog codes, PSM control. So this is the digital PSM main block: input output declaration, register wire declaration, parameter declaration, and output voltage, and then error generation. And we have two blocks here. So if I talk about these two blocks, the clock generator is exactly same as the voltage mode control, current mode control. Only difference is we have this PSM logic. So this is the new block that we are going to discuss. Clock generator is just copy paste of what voltage mode control and current mode control blocks are. Followed by the transient. Again, it is that's just the copy paste. But in the case of PSM, we are not giving any load transient because it is a light load condition modulation technique. So it will happen only at light load condition. For high load, we will not use PSM. So for high load, we use voltage mode control or current mode control. So there is no question of transient, but it is there in the code, but we are not using it. So it has two subblocks. One is clock generator, which is exactly same as voltage mode control or current mode control. The other one is the PSM logic. So let me come back here. So the main module has two submodules. One is clock generator and another one is the PSM logic. So we will discuss about this. This is the new block. So we will discuss about this. The other part, the rest of the part are same as voltage mode control and same as current mode control. Okay. So now let me go into this PSM logic. Before we go into the code, let me just show what is there. Again, input output declaration, wire edge declaration, and it has two parts. One is the PWM duty generation, another one is the PSM logic generation, and this is the output. So it has two blocks, right? So what are the two blocks? One is the PWM generation. So if I use a different color, say this color. So this is the PWM generation. So it has two blocks, right? PWM generation and PSM logic. And if I use yellow color, this entire D flip-flop is PSM logic. So the same will be implemented in the Verilog HDL. So PWM generation means it will generate a fixed duty ratio pulse. PSM generation means it will give the output either 0 or 1 depending upon the V naught is greater than V reference or less than V reference. So let me quickly go through the code. So PSM logic, as we have discussed or shown in the code, initially it will have the declaration of inputs, outputs, wire and register. And how many inputs it have? F clock and FPWM are the input. NRR is all the input. Duty and QHQL are the output. So it has two subparts as we have discussed. One is the PWM duty generation, which is the fixed duty cycle generation. So what we are doing, we are giving clock or FPWM, and again we are using the counter. So I'm not going into the detail. So the output is like this. So this is DT. This is also DT. And this is T. So what it is doing is it is generating a fixed duty ratio, fixed frequency gate pulse, which is named as QPWM. So this is the PWM generation. So this is the QPWM. If we map it here, this is the QPWM that we are generating in the PWM generation block. Now PSM logic will see whether V naught is greater than V feedback, and then it will give to QPSM. So coming to the PSM logic. So PSM logic, so an error is n reference minus n out, right? So an error can be either positive or negative. When it is positive, when it is negative, it is positive when n reference is greater than n out, and if it is less than 0, it is n reference less than n out, right? So when n reference is greater than n out, what should happen? It should skip, right? Because, or it should charge. It should charge. So in this condition, it should charge. And in this condition, it should skip. And how do I check an error is positive or negative? I'll check the most significant bit. I can see the most significant bit, right? Which is an easy logic. So I'll check the most significant bit. If it is 1, then it is negative. If it is less than, if it is 0, then it is positive. So I'll check if an error is 9, which means it is negative. So if it is negative, it should skip, which means QPSM should be 0. And else means an error most significant is 0, which means positive. If what is positive mean? Positive mean that n reference is greater than n out, which means charge pulse, which means QPSM is 1. So which means QPSM is 1. So if I have to summarize, it has two things. One is skip pulse and the another one is charge pulse. So PSM logic generation has given QPSM. Now if I go back, there is an AND operation. Let me use a different color. There is an AND operation for QPSM and QPWM, which will generate say Q. And then it is going to dead time. But in the case of DCM operation, QL is always 0 because we are giving QH and then we are turning off. Then it will come back to 0 and it will remain. So the diode will conduct, and so there is no question of dead time. So we are giving QH as QPWM and QPSM. So whenever QH is on, it will increase, and then QH is off, and then QL is always off. So it is becoming 0 and it is staying there because only the diode is conducting. Is this like code clear to everyone? Hello?
Sir, but here,
Yeah.
sir, can you hear me?
Yeah. Continue.
Hello?
Yeah.
Sir, in this case, for that skip QPSM less than or equal to 0, sir, here instead of less than or equal to 0, if you put just equal to 0, it also
works.
same
It
meaning,
also
right?
works. Yes.
Okay.
So
The code is understood, sir.
yes, one student has asked why an error of 9. So an error of 9, if it is 0, so it is a single bit. So it can be either 0 or 1. So an error 0 means an error 9, most significant bit 0 means an error is positive. If it is 1, an error is negative. So again, this will map to the first line and this will map to the second line. And one student has asked, is PSM in DCM mode? Yes, it is in DCM mode. So this is DCM mode and this is for light load condition. So this is a simple logic, and there is no DPWM because we are not even using QL. It is always 0. There is no question of QH and QL becoming 1 at a time. So there is no dead time requirement. Coming to the hardware results. Yeah.
Sir, we will skip the successive as far as this n reference is greater than n out.
Yes.
We will be skipping the pulses, successive pulses.
Yes.
Only when if it comes less than n reference comes less than n out, then we will start giving the pulse.
Yes.
Okay. Okay, sir.
Okay. So let us quickly go through the hardware results. We have another question. Sir, I have one basic doubt. Can we use Arduino to implement this? See, you can use any digital architecture or any digital component that you have, you can use this. The logic will remain same, the architecture will remain same, only the coding part varies. So you can implement this in microcontroller or any other tool. But if I do not know whether Arduino has ADC, DAC comparators, if it does not have, then you might need a signal conditioning board. But as far as you can write a fixed point arithmetic code in any one of a microcontroller or Verilog, you can still be able to implement the digital controller. Only it will have some different syntax. You have to follow their syntax. So here, if you see, we have V in 6.4 volts and V in 7 volts. So these are the charge pulse. So during this charge pulse, it is charging so much that the rest of the cycles it is skip, and again it is charging, and here also it is charging, and these are skip pulse. So if I increase V in, then my ripple will increase, right? So if ripple increases, we are injecting more charge. Injecting more charge. So if we are injecting more charge, that means we have to wait until the charge is dissipated, which means our skip pulse will increase. So compared to here and here, we can see the skip pulses has increased, and it is also like not as in a periodic way. Here it is 2, here it is 1, here it is 2. So there is no such periodic fashion that is in which it is happening. So it is charging here, discharging here, here charging only once, discharging again, here it is charging twice, and it is discharging. So if we increase V in, more charge will be injected during the charge pulse. So the skip pulses should increase. So it will wait for longer time so that charge will be dissipated, and then again it will charge. And this is the duty ratio command that has been considered. So we know that this is the V ramp, right? So this is the V ramp, and this is the VCon. So what they are doing is they are comparing this VCon with the V ramp. So we know that, let me use a different color. We know that V ramp is of 2 volt. And what is the analog quantized voltage? It is 0.25, right? There is less than a minute. If this meeting ends, kindly quickly join. We can continue our discussion. And VCon is 0.25. So what is my duty ratio? My duty ratio is 0.25 by 2, which is 0.125. So that is how I'm getting the duty ratio. So we are giving a fixed duty ratio of 0.125 pulse for charge pulse as well as skip pulse. As the duty ratio is same, if input is increased, the ripple will increase. So we are injecting more charge, and skip pulses will also increase. Until this point, is it clear? I think the meeting will end. You quickly join. We can continue the discussion. So this is when we are increasing V in. So what happens if we decrease V in? So when we decrease V in, the ripple will. So what is happening here is we are injecting less charge. So as we are injecting less charge, it needs more charging pulses to increase its charge, and hence the skip pulses will reduce. So skip pulses will reduce. So when we decrease the input voltage, the skip pulses will reduce because the injected charge in the charge pulse is so less that it will discharge quickly. So we have to charge it more times, and that's why skip pulses will reduce. So what happens if I reduce V in below some threshold voltage? So what happens is here zero skip pulses. Zero skip pulses, all are charging pulses. And still, because all are charging pulses means V naught or V out is less than V reference. Because the duty ratio provided, the duty ratio is not sufficient. because whatever duty ratio that is provided, or whatever charge that is being injected is not sufficient for the converter to raise the voltage more than V reference. And that is why here there is no regulation, because it is not able to provide enough regulation that it is not even crossing V reference, even though we are using the charge pulses. So in such cases, what we have to do, we have to increase the duty ratio so that we can inject enough charge and it will cross V reference and there will be some skip pulses. So the same duty ratio that we have discussed in the last slide, which is 0.125, has been considered here. And here there is no voltage regulation. So how we can improve this? We have to change the duty ratio accordingly, and we have to use adaptive duty ratio. And all these control techniques and issues related to this are discussed in SARS papers. So we are not going into this. So if you are interested, you can go through this. Here link is embedded. This is not mandatory, but if you are interested, you can go through these papers. So this completes our week 8 topic. So just to summarize.
Sir,
Yes.
sir, in last case, it will be 0.128, right?
Yeah, actually, VR is not exactly 2 volts. It is slightly less than 2 volts. So D will be somewhat more than 0.125. So it is around 0.128 that SAR is getting.
Yes, sir. Yeah, because you have one here in this digital representation.
Uh-huh.
We have one after 0, which is
Yes.
128 of digital result.
So this is 0.5, 0.25. This is 0.25, right? Do you agree? This is the dot 0.25. Hello.
Okay. Yeah. Yes, sir. Yes, sir.
Yeah. So
Because it is 2 power minus 2.
yes. So we are comparing
Okay.
this 0.25 with the ramp voltage of 2 volt. So the duty ratio will be 0.25 by 2 volt, which is 0.125. But VR is slightly less than 2 volt, not exactly 2 volt. So duty ratio will be slightly more than 0.125. So SAR is getting around 0.128. But just for ease of understanding, we are considering it nearly 2 volt. So duty ratio will be close to 0.125. But this is just to make you understand how we can get the duty ratio. But depending upon these values, duty ratio will vary. So just to summarize, in week 8, we have discussed 3 control techniques. One is the digital voltage mode control, and the other one is the mixed signal current mode control, and the other one is the digital PSM. So we have considered their top-down design method analogy or top-down design methodology. And then we had discussed their Xilinx ISC, Verilog HDL code. And then we have seen Xilinx ISC. We have not seen the simulation, but we have seen the hardware results directly. So now let us solve a few problems. So I have given you a digital voltage mode control, and I have given the Q format of KP is 4.6, Ki is 1.9, KD is 4.6, NE is 1.9. So what is the Q format of NPROP? What is NPROP? NPROP is KP star NE, right? So what is the Q format? 4.6 star 1.9. Hello.
4.15, right, sir?
Yes. So what happens is it is 5.15, which should be again converted to 4.15 because it is redundant. Now, if we go back to an integral, which is Ki star NE. So what is it? Q1.9 star 1.9. It will be Q2.18.
1.8.
Yes, so it is 1.18. And later, if we want to change it, then so that the addition can happen. So then we changed it to Q4.15. This is for our next operation, but when we ask the Q format, we'll say 1.18. Now KD is similar to KP. because the Q format is same. So what we'll get 5.15. And after that, there is one redundant most significant bit which we'll remove. So we'll get Q4.15. And ncon, what we do in ncon, we'll add all these things by making the Q format same. So 4.15. Now we have made it 4.15, 4.15. So it will be 4.15. So that is the Q format of ncon. So this is how we calculate the Q format. Is this clear until this point?
Yes, sir.
Okay. So yeah, hello.
Yes, sir. Yes, sir.
Okay. So now coming to problem 2. So problem 2, I have given KP, KI, KD values, and I am asking the 10-bit binary representation, and Q format is given. So if it is 4.6, I have 4 bits decimal, 6 bits, 6 bits decimal and 4-bit integer. So it is 2.5. So 0, 0, 1, 0. This is 2, right? And 0.5 means 1, 1, 2, 3, 4, 5. Understood how I'm getting this?
Yes, sir.
Yeah. Now 5.5. So there are 5 bits integer, 5-bit decimal. So what happens? It will be 0, 0, 0, 0, 0, 1, 0, underscore 1, 1, 2, 3, 4. So what has changed? Here it is 5 bits. Again, here it is 5 bits. Here it is 6 bits. Here it is 4 bits. So now the dot is here. So it is Q5.5 format. The value is 2.5. And coming to KI. So I think K, okay, just let me calculate. I think Ki is 2 to the power minus 3 plus 2 to the power minus 4. Yeah. Let me check. Yeah, 0.1875. So I have made Ki in such a way. So this is 2 to the power minus 3 plus 2 to the power minus 4. So I have minus 3 bit and minus 4 bit. So 1.9. So 1.9 means 1, 0 and decimal. 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4, 4 bits. 1, 2, 3, 4, 5. Understood how I am writing this? Hello.
Yes, sir.
Yeah.
Yes, sir.
So this is 1
Yes,
bit.
yes.
These are 9 bits. Now I have 2 integer bits, but my Ki is decimal. So there will be no integer bits, 2 zeros, 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4. How many bits are done? Out of 8, 4 are done. So 4 zeros. 1, 2, 3, 4. Yeah. So if I say 2.8 bit, so this is 2 bit and this is 8 bit. So okay, let me also write this. 2.5 is 2 to the power 1 plus 2 to the power minus 1. And 5.25, we'll use some other color, maybe green color. This is 2 to the power 2, 4, 2 to the power 0, 1 plus 2 to the power minus 2. Okay, so it has 4 bit. 4 bit means most significant bit 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. So now it is 5. Now underscore
0, 1, 4 zeros.
0, 1, 1, 2, 3, 4. Yeah, right. So again, we have 4 bits here, 6 bits here. Now, if we do the other one, we'll have 1 additional 0. So 1 0 will be removed here and 0 will be added here. So 0, 0, 1, 0, 1 underscore 0, 1, 1, 2, 3. So if you see here we have 5 bits, here we have 5 bits. So similarly, if I give these numbers, accordingly you can calculate the KP, KI, KD values. But as writing the binary from the decimal is a bit tricky, so that's why I have given this example. But if I given you binary and if I ask you to get the decimal, it is just simple part. You have to add this with the signs and considering the dot sign. So that would be somewhat relatively easy. So I think that you will be able to do easily. So that's why I'm not discussing it here. So now what I have given, so this is another good question. So here I have given 100 megahertz clock frequency, and I am using a counter based DPWM. So I'm using a counter based DPWM, and I want to generate 1 megahertz clock from this F clock. So what should be the value up to which the counter should count, which mean to say n count. So what is my n count?
Count
How
is
can I get this?
100 megahertz by 1 megahertz.
Yes, so actually n count plus 1 is F clock by say F clock by whatever this frequency, say FSW1. So it is 100 megahertz by 1 megahertz, which is 100. So what is my n count value? So my n count, say I want to say n count 1, as there are two parts. So n count 1 is equal to 99. So it will count from 0 to 99. So in the second part, it is the other way around. So I have given you the
N count here.
n count here, and I'm asking you what is the frequency. So n, let me use a different color. So n count 2 plus 1 is equals to F clock by FSW2. From this, I'll get FSW2 is F clock, which is 100 megahertz by 4 plus 1, 5. So from this, I'll get FSW2 is.
So you asked for the clock frequency.
Yeah, sorry.
Second question, we have asked for the clock frequency.
No. I'm asking what is the frequency of clock generated, or the pulse generated, not the clock frequency. Like this is that is being generated using this counter. So here it is 20 megahertz. So is this question clear to everyone?
Yes.
Okay, so we have a question here, 20. Yeah, 20 megahertz. You are right, Shankar. So this is 20 megahertz. So these are the type of questions that you can expect from this. Majority, some other questions could be understanding the architecture. So I think some of the questions are like find the missing block. So you should be understanding the architecture, and then you will be able to find that missing blocks. These type of questions are given in assignment. I hope this will be able to help you solve them in a better way. So with this, we can conclude the session. If you have any doubts, you may ask. If you do not have any questions, then we can conclude this session. So I'll keep this.
Good night, sir. Thank you.
Okay, yeah. Okay. Thanks everyone, and good night.
Sir,
Yeah.
sir, in exam, how many, what is it, formulas we are going to remember, sir?
Like
This is the
what?
first time I'm taking this course.
Okay.
Verilog HDL is very new for me.
Okay. Like we will not
Think,
be asking you to write the HDL, but maybe we'll be asking you to we will, if we ask you to write the Verilog HDL, we will give you the options, and you have to select the correct Verilog HDL one.
yes, sir, okay, sir. By practice, we are making it into.
Yes, say the question gives you some gates: AND gate, OR gate, XOR gate, and there are three such gates, and there is some output. So we will
The
ask you.
problem at all easy, sir. We can understand, we can solve it. This and this Verilog problem are very easy for me. But that overall, I don't know how to face the exam.
No, like don't be afraid. We are there to help. So like the plan is like this. So every week I'll be taking sessions on these things, and at the end I'll take a session before your exam. So maybe at that time I can give you more insight on like what type of problems you can expect in the question paper. But if you able to solve all the assignments, then you will be able to solve around 80% of the questions in the question paper, because whatever
Assignment and all we are solving, sir, by referring the sir
lectures.
videos. Yes, sir. then only I can able to solve it, sir.
Yes, yes. So
So
it
how I'm
is,
going to remember all those things?
yeah, it is like some if you consider the controller design part where we have given GVD, GVC. So those transfer functions, the ideal transfer functions without any parasitics, you can remember, and you can always refer to SAR's lectures to get that expression. But in the like final exam, it will not be
Lot of
more like formula
formulas
remembering.
we have to remember, isn't it, sir?
Yes, yes.
Lot of
So
formulas, the key
yes.
points we have to keep it in mind.
Yes, yes. So like I'll give you one question, say voltage mode control or current mode control, pole zero cancellation. So if I give you a PI controller, and if you know the GVC of S, then you can calculate the KPKA expression. So you need not remember KPKA expressions, but you should remember GVC of S, from which you can get the KPKA. So you need not remember KPKA, but you have to remember GVD of S. So only those parts which you need to remember, from which you can derive the other expressions. So you can like prepare in that way. So you can remember GVC of S, but if KPKA are asked to be found, then you can derive KPKA expression, and then you can get the KPKA values. But in the case of Verilog, we will not expect you to like remember all the each and every
You
line.
never expect write the program and all.
Yes, yes. So either we will give you a code and we will ask what it represents. Does it represent any and
This
get
kind of
not get?
problem and all, okay, sir, we will manage.
Yes,
I will
yes.
manage.
Yeah. Yeah. So 80% of the final question paper exam will be based on the assignments. So if you thoroughly solve the assignments, then you will be able to solve 80%. But remaining 10-20% will be somewhat tricky and difficult questions. So, but 80% of the questions you will be able to solve if you follow the assignment. And I'll also be taking one extra session where we'll solve some key problems throughout the entire week, or if you have any questions, then we can discuss. So after week 12, I'll take another 1 hour session where we can discuss few problems, or we can discuss your queries.
Okay, okay, so thank you, sir.
Okay, thank you. So if others have any doubts, they can ask, else we can end this session.
No, sir.
Okay,
Bye.
okay, okay. We are ending this session. Thank you. Good night, everyone. Bye.